Hi, in this video we're going to do a sand casting example problem of this small ring-shaped device. The problem statement as well as the final dimensions that we want are given here. You can pause the video and read over that if you need to for reference. In this video we'll go over parts A, B, and C, and in subsequent videos I'll go over the additional parts. For right now, I'm going to get rid of the problem statement, so if you need it, it's your last chance to pause the video. Now, as stated in there, there's a machining tolerance as well as a casting tolerance that we need to take into account. And it asks us to sketch a rough, approximate schematic for what this might look like when we cast it. So essentially, you're going to balloon up the device, taking into account both the machining and the casting tolerances. Right? So this is what this is approximately look like. It's hollow in the middle, and we do take into account the draft 1/4 inch per foot on both edges here. All right? Main dimensions that we're going to need to calculate here. Let's look at the bore, which we want as 4 inches. As the final, to take off 0.06 inch off the inner two sides for machining tolerance, as well as a 0.08 inch for the casting tolerance to give us a inner bore diameter of 3.8 inches. All right, so that's right here. 3.8 inches. All right. The outer diameter, we want this to be 6. We're going to add on, again, making this more material. The outside, both edges that need to be machined, so that's 2 times our machining tolerance, plus our casting tolerance for 1 overall dimension. So that's our 0.08 inch, gives us 6.2 inch outer diameter. All right. The height we want to be 1 inch. We're going to add on, again, you're going to machine off the top face and the bottom face, so add on your machining tolerance plus the overall casting tolerance, 0.08 inch, for a 1.2 inch height. All right. Other dimensions that we might need to take into account. This one will come out to be 4.7 inches. Right, this one we already said the bore was 3.8. This height here comes out to 0.39 inches. All right, and last was this radius. We want 0.75 inches as specified. Thank you for those students who pointed out my mistake today in class. I had originally added this for your machining tolerance, should be subtracted. So thank you for those of you that pointed that out. Inch, so this should come out to 0.69. This is referring to that radius on this edge, and on this edge you want more material here so that once you machine out, you are left with a radius here of 0.75 inches. So you start with a 0.69 inch radius. All right? So these are your approximate dimensions that you will need from casting and machining tolerances. Now, where should we put the parting line for this? Around the thickest part here, approximately, would be the best place. It also says in the guidelines to keep it as low as possible. Well, if we put it any lower, we're not going to be able to get this thing out unless we destroy the mold. So approximately here is about where you want to put the parting line. All right. The top part will be your cope, and the bottom part will be your drag side for your casting part. All right. We also need to take into account, if we weren't going to be taking account with our tolerances, volumetric shrinkage. So let's look into that. So I can look up in a table using the material we've got, volumetric shrinkage. Comes out to about 7.2%. All right. For a single dimension, take the cube root of that, we have about 1.93% shrinkage per dimension. That means whatever you start with, that dimension is going to shrink by just under 2%. And then after that, we want our final dimension. All right? So if we were to take into account the volumetric shrinkage by having more dimension in this manner, and then have it end up being our final dimensions as specified here, right? We would need to compensate by getting this thing to be larger than the final value we'd want, let it shrink, and the final value would be as desired. So if we were to do that, what would we want? So we'd want an initial dimension that we don't know, right? It would shrink by 1.93% approximately, right? And that would leave us with a final dimension that we desire. So right now we'll call this 1. All right? So if we want this, this is our unknown. Let's move this term to the other side. All right? All right, so this is essentially saying that that initial dimension needs to be 1.97% larger than the final dimension we want, so that once it shrinks by a value of 1.93%, it will end up being this final dimension. So this is one way to take it into account. This is another way to take it into account. All right? So we're going to stick with this method from here on out. All right? But this is two different ways to do this. Now the last part of this problem was part C, which says, how would you sketch out a manner of doing multiple parts? Right? So this is one part, and I wanted to do 6 of these. Well, I would need a sprue. And I would need this sprue to go through a runner. Right? And at some point, I would need this runner to come off. And let's have a part. And this runner is going to come off and feed this part. right? So this is one way to do this. And this is not the prettiest thing, but this is a schematic to show you the method here. So I'd have a part, right? And I have this runner system that could go off to another part down the line, have other parts. I could have this maybe comes in and they radially split into 6 parts. Doesn't matter. This is not the only way to do this. This is one way to do this. But the key concept here is I have a sprue that comes in, right? It has a cross-sectional area at the sprue. We'll go over this more in the next video, right? And I have a gate here that tapers, feeding my part. We'll calculate that in the next video. But this is one way for a single sprue to feed multiple parts.